Hello, my name is Haulana Matamonaisha, and I'm going to present a semantic-aware multimodal data warehouse for crowdsourcing and contextualizing AI-generated educational content in fragile contexts. We are a team of 3 from Makerere University. So the problem, refugee learners often study in environments with limited educational resources and disrupted learning. There's poor internet connectivity and culturally diverse communities, as we know, refugee camps. So existing digital tools have tried to solve the problem, but however, most content generated is generic and not adapted to the learner's local environment. For example, lessons may contain unfamiliar examples, objects, or cultural references that the learners cannot easily relate to. So even though generative AI is transforming education, many systems still fail. They lack cultural awareness and depend on generalized internet training data and produce non-contextual educational outputs. And this problem led for a need for a structured, context-aware, multimodal, context-aware data systems. So to achieve this, our research combines several important concepts, which are summarized in these keywords. So starting off with a semantic data warehouse. So a semantic data warehouse is one which stores data and the meaning or the relationships behind the data. Then crowdsourcing, this refers to collecting images, videos, and educational content directly from the local communities. Then fragile contexts, these are low resource communities. Excuse me. These are low resource communities that are affected by challenges like displacement, poor connectivity, and limited educational resources. Then multimodal AI. Multimodal AI is AI that can understand multiple types of data, such as text, images, audio, and video. Then knowledge graphs. Knowledge graphs, these are semantic networks that connect related concepts, regions, media, and curriculum content. Then the epistemic trust. The epistemic trust is deals with ensuring AI-generated lessons are reliable, culturally appropriate, and factually grounded. Then the neurosymbolic content generation. This refers to combining multiple AI models with symbolic reasoning graphs and rules for better contextual understanding. Then accelerated education programs. These are programs that are designed to help learners that have taken time out of school to learn faster, to catch up faster. And then, so we did review existing research systems related to multi-agent AI, semantic retrieval, educational AI, and knowledge graphs. So our purpose here was to identify what current systems do well and where the research gaps still exist. So we started off with a Mac SQL. So this it uses multiple AI agents to improve reasoning and query accuracy in structured databases. However, it focuses on SQL environments and does not support multimodal educational content generation. Then we did look at the structure, which improves AI reasoning using the structure-aware techniques, but it depends heavily on predefined schemas and limited adaptation to fragile educational contexts. Then the Gen Mentor, which focuses on the personalized learning multi-agent tutoring systems, but it focuses more on the learner modeling than the semantic educational infrastructure. Then we looked at RAG systems. So this improved the factual grounding by retrieving information before generating responses. However, the traditional RAG systems mainly work with unstructured text data and contextual educational grounding. Then the knowledge graph systems, this improves semantic reasoning by connecting related concepts and entities, but they're often a little bit too complex for for fragile contexts and low resource settings like refugee camps. Then multimodal AI, these systems support learning using text, images, audio, and video, but many are not powered with semantic warehouse integration and curriculum alignments. Then crowdsourced educational systems. So these improve diversity of educational knowledge and community participation since they collect images and videos from the communities. However, ensuring consistency and trustworthiness remains a major challenge. And then moving on to the computational problem. So here we explain the complexity of our system and why a traditional database architecture is not sufficient for this problem. So the L0 educational localization. So the foundation of the problem is generating educational content that is contextually relevant and trustworthy for refugee learners. Then L1 weak supervision. So the system learns from crowdsourced media, metadata, and curriculum alignment signals instead of relying on fully labeled datasets. Then the multimodal retrieval and generation. So the architecture retrieves contextual multimedia information before generating educational content to improve relevancy and consistency. Then the unstructured multimodal data. This is also the system uses highly unstructured data such as videos, images, text, and localized text. So then this new multimedia content is continuously uploaded and semantically processed and integrated into the warehouse. So the system must, the L5, this is the system constraint, it must be able to handle culture sensitivity, prevent hallucination, and pedagogical validity, and low resource infrastructure constraints. So for the decentralized edge-to-cloud architecture, the L6, the architecture should support intermittent connectivity, distributed contribution pipelines, and edge-based processing. Then the neurosymbolic multi-agent models, the system combines LLMs, VLMs, and graph-based symbolic reasoning to improve like the contextual educational content generation. And then the technical justification. For this work, traditional relation databases struggle with multimodal semantic relationships and decentralized synchronization challenges. So therefore, this research uses a semantic-aware graph-oriented architecture instead of the relational system. And moving on to the research questions and objectives. And so here we present the main objectives of our research and the key questions that guided the design of our system. So the objectives for this research was to enable textual contextualization for educational content, enable visual contextualization for the image and for the video and image generation models, and to also ensure alignment with a competence-based curriculum. And then we were supposed to provide, the goal was to provide scalable warehouse designs for multi-region deployment. And then the first question we had to ask ourselves was, for the research questions, which curriculum competences already have contextualized examples. So this is to help us evaluate the availability of grounded educational content within the system. Then secondly, which regions are well represented and which ones are underrepresented. This is to help us identify the data imbalance and contextual gaps across the different refugee communities. Then the third question is, are uploads producing the complete semantic descriptions and tags? This evaluates the effectiveness of the semantic extraction pipeline. Then finally, how many contextualized lessons has a teacher generated? This supports the semantic analysis and educational monitoring within the platform. So overall, these objectives and research questions guided the development of the system capable of generating scalable and context-aware curriculum-aligned educational content for fragile contexts. So moving on to the methodology. So our methodology is simply a multimodal semantic engineering approach. So first of all, here, so the process begins. I'm going to take us through like the step-by-step architecture from uploading an artifact to the final lesson generation output. So the process begins with teachers and community contributors uploading local images, videos, and educational material from refugee settlements. So these uploads help provide real-world contextual information from the learner's environment. Then these uploaded artifacts and multimedia files are stored in Superbase bucket storage, which acts as the centralized multimedia repository. So this supports the scalable storage and management of the unstructured multimodal data. Then from this, we move on to the semantic extraction and annotation. Then, so here we have AI models that analyze the uploaded media to extract the semantic meaning. The system identifies objects, environments, the cultural artifacts, the learning material, and the contextual relationships. So these are converted into semantic tags and annotations. From here, we move to the Neo4j knowledge graph and the vector retrieval. So the semantic information is then stored inside the Neo4j knowledge graph and the vector retrieval system. So this enables the semantic reasoning and contextual retrieval based on the relationships rather than simple keyword matching. So then we move on to the curriculum grounding. So the retrieved context information is connected to the Uganda's competence-based curriculum framework. This ensures that the generated lessons remain educationally aligned while still reflecting the local context. Then the contextualized lesson generation. So finally, the multi-agent AI system uses the semantically retrieved contextual evidence to generate the localized educational content. So this helps to produce lessons that are culturally relevant, visually grounded, and easy for the learners to relate to. So in summary, we transform the raw community data into structured semantic units that support trustworthy, context-aware AI, educational generated content. So moving on to the research contributions. So here we highlight the major contributions of our research, what makes our architecture unique. So first of all, we have the ontology multimodal semantic data warehouse. So we designed an ontology-driven multimodal data warehouse, which allows the system to organize and connect text, images, video, curriculum content, and semantic metadata within one unified architecture. Then the offline fast semantic ingestion pipeline. So second of all, we developed an offline fast semantic ingestion pipeline. This is important because refugee environments often have unstable internet connectivity, and the system can continue processing and storing semantic information even during those connectivity interruptions. Then the neurosymbolic and multi-agent grounding framework. So we proposed the neurosymbolic multi-agent framework, which combines AI generation models with symbolic reasoning using knowledge graphs and semantic rules. So This improves the contextual understanding, curriculum alignment, and reduces hallucination in generated educational content. Then there's semantic business intelligence and provenance traceability. So finally, we introduce the semantic analytics and provenance traceability to allow educators and researchers track where the contextual knowledge came from, how it was processed, and how it affected the lessons that were generated. So moving on to the data set and the knowledge graph description. So our data set combines structured curriculum content with the crowdsourced artifacts from refugee settlements, the AI-assisted semantic extractions, and the localized images into like contextualized semantic warehouse records for the educational grounding. So starting off with the curriculum corpus, so the system uses structured Ugandan curriculum content as the formal educational grounding layer. And then we have the uploaded local media, so the community contributors upload the local images, videos, and refugee settlements, like to provide the real contextual evidence. Then the semantic annotations, the AI models generate semantic descriptions and tags from the uploaded media for retrieval and analytics. Then the graph records, the knowledge graphs connects the curriculum concepts, region, method, media assets, and the semantic tags through semantic relationships. So the knowledge graph acts as the semantic memory and contextual reasoning layer of the system. So moving on to the AI. So this is again an explanation of our methodology, sort of like our pipeline, the full architecture, as I had given us a walkthrough earlier, and so as I had given us a walkthrough earlier for our architecture. So what I can briefly say, so step one, we upload the data from the communities, and then step two, the AI analyzes the data, generates the semantic extractions. Then after we store these semantic extractions, then we link the curriculum, we connect the uploaded local evidence to the Ugandan curriculum, then we move on to the semantic retrieval until like the final lesson generation. And then moving on to the AI models and the mathematical formulations. So so in here, I'm going to briefly talk about how the AI models used and how the semantic retrieval generation are mathematically performed. So first of all, I'll start off with a vision language model. So we use a vision language model to analyze the uploaded images and videos to extract the semantic descriptions and the tags. Then we have a transformer LLM. So we use a large language model for contextual lesson generation and semantic organization. Then we had the embedding model, which was the first embed that converts the curriculum text, semantic descriptions, and queries into vector embeddings for semantic retrieval. Then the cosine similarity, which is used to measure the semantic closeness between the embeddings and what was happening during the retrieval. Then the Neo4j knowledge graph, it constrains the retrieval using regional and semantic relationships for the generation. So overall, the architecture combines VLMs, the LLM, the embedding, and the graph retrieval into one hybrid semantic pipeline. And then moving on to the business intelligence. So here I'm going to explain how the warehouse supports the semantic analytics, the explainability, and the educational monitoring. So the system tracks where contextual evidence came from and how it influenced the generation of outputs. Then the curriculum coverage. So the warehouse can identify which competences already have contextualized examples and which still lack coverage. Then regional analysis. The system can analyze which refugee regions are well represented and which ones are underrepresented. Then the culture validation. The warehouse supports monitoring. It supports monitoring culturally validated contextual content. So the BI layer transforms the warehouse into an explainable, governable educational system. And so moving on to the evaluation, benchmarking, and governance of results. So here we basically going to talk about how we evaluated the accuracy and robustness of the system. So the VLM was evaluated using a precision, recall, and F1 score against the human expert annotations. And the result, the system achieved a high macro average F1 score of approximately 0.80 across the different held out refugee regions. And then the zero-shot evaluation, the lesson generation pipeline was evaluated using the region held out testing instead of like using random splits. And then the generated lessons were evaluated based on curriculum alignment, culture grounding, and hallucination avoidance. So overall, I would say the results show that the retrieval grounding improved contextual accuracy and reduced hallucination. So moving on to the data ops and the edge deployment and edge orchestration. So, so first of all, we considered an offline first architecture. So the system is designed for low resource environments with unstable internet connectivity. And then for the edge processing, we have lightweight processing and multimedia handling can happen locally before the synchronization happens to the cloud. And then the cloud assisted AI, heavy AI processing such as semantic extraction and generation is performed during the hosted model operation endpoints, and then caching and optimization. So the embeddings and the semantic outputs are cached to reduce the repeated computation and bandwidth usage. Then provenance logging. So the system records the model versions, prompts, and the semantic outputs for traceability and reproducibility. So the architecture balances scalability, low resource deployment, and AI governance. Then briefly talking about the limitations and the architecture failure modes. So the vision language models often misinterpret the culturally specific objects and activities. And then the new refugee regions initially lack enough contextual media for strong retrieval grounding. And then we had bandwidth constraints. So uploading multimedia content in low connectivity environments and slow synchronization. Then the semantic fragmentations. Similar regional concepts may appear as separate graph entities if the semantic normalization is weak. So most failure modes are related to the data sparsity, cultural ambiguity, and low resource deployment conditions. Then the conclusions and the future work. So this project proposes a semantic-aware multimodal data warehouse for educational content generation, AI generation in fragile learning environments. So our main achievement, the architecture, it successfully combined multimodal AI, semantic retrieval, knowledge graphs, and curriculum grounding into one unified educational system. So the main contribution is that the system improves contextual relevance, culture grounding, and epistemic trust in AI-generated educational content. So our future work will focus on improving the lesson generation stability, increase regional media coverage, and strengthen semantic normalization, and deploying lightweight edge AI models for offline usage. So overall, this research demonstrates how semantic AI infrastructure can support culturally grounded education in low resource environments. So these were our references, the different papers that we went through to further guide our decisions. And we would like to extend our appreciation to Mr. Galiwango, our supervisor, the Courses Rights Fund, and different collaborators in the teaching fields for technical feedback, and of course ourselves for the great work. Thank you so much.